All right, here we go with Unit 5. We're on Topic 3, which is the concentration changes over time. So far in this unit, we've done things a little bit out of order, but we've looked at what a reaction rate is, how to determine the order of a reaction through a couple of different methods, looking at the rate law, determining the rate law. We've also looked at just basic reaction profile graphs, looked at activation energy and collision theory, so kind of the basics. So now we're going to take a look at, we've looked at the rate of a reaction using a rate law. So it says rate laws so far have allowed for the calculation of the rate of the reaction from the initial concentrations of our chemicals and the rate constant. Okay, so that's K, right? Rate laws can also be written to show the relationship between the concentrations of a chemical and time. So these are known as the integrated rate laws. Now, if you're one of my calculus students and you are taking that right now, you are probably getting towards this topic in your calculus class called integration. So the integrated rate laws do bring in calculus, but they've done the calculus for us and it spits out a new equation and we just have to use this new equation. So don't get freaked out by that word. But if you are in calculus, you'll start to see some things that are similar here, or some patterns, and something to keep in mind and see that connection between the two courses. So the integrated rate laws are new equations that were derived to help determine the concentration of chemicals at different times in a reaction, right? We don't always just want to know the initial rate of the reaction. We also want to know how the concentrations change over time. These are equations given on the AP exam equation sheet, but were derived using calculus. Like I said, you will only need to know these equations, how to use them, not to derive them. So to give you a little preview, you should always check out your equation sheet. Sorry for the reflection there. But these are our equations for kinetics. It's on the bottom of the front page. Let's see if I can, there we go. That's a little easier to see. So we've got three of our integrated rate laws, and then we have this half-life equation. So they remind us over here that K is our rate constant, T is time, and then what half-life is. So we're going to be visiting these equations, learning each of them with examples, and going from there. So we're going to start out with zero order. So zero order reaction rates do not depend on the concentration of any reactant. If the concentration of a chemical is zero order, changing its concentration will not affect the rate of the reaction. The rate is basically constant. So on that equation sheet, the first equation given in that kinetics section is the integrated rate law for zero order reaction. So we're going to write that down, copy it down. So it is the concentration of chemical A. It looks like this pen is dying. Let's switch it out. All right, concentration of chemical A, and it has a little T at the bottom, minus the concentration of chemical A with a little 0 at the bottom, equals negative K, our rate constant, and T. So let's talk about what all of these variables are. We've got 4 different variables in our equation. So A with a little 0 is the initial or starting concentration of our chemical. So at time 0, which is why there's a little 0 there. So our concentration at that initial time. AT is the concentration of a chemical after a time has passed. Okay. K is our rate constant. Okay, and since it's zero order, okay, your rate constant would be in molarity per unit of time, sometimes seconds, minutes, years, whatever that time period is. And then your time is T. So whatever time this is, say this is the time after 30 seconds. This would be your concentration at 30 seconds. If your time was 50 hours, then this would be your concentration at 50 hours. Okay, so you don't have to change anything about this T and the 0. It's just saying initial and final. And you'll notice it's final time or final concentration minus initial concentration. We've done final minus initial for a lot of changes. Okay, so that's the change in concentration equals negative KT. So this equation can be used to solve for a lot of different variables, any of these variables. So the concentration of a reactant remaining at any time after the reaction begins. So if we know the initial concentration and our rate constant, we could figure out the concentration at any time we desire. The time required for a specific amount of reactant to be used. So if we want to know, okay, here's our initial amount, how much time does it take for it to be a fourth of that amount, or to be 0, anything like that. And then the rate constant, we can also find that. Now this is not an exhaustive list. We could also, given all the information, we could backtrack to figure out an initial concentration, all that. But we can solve for any variable here. So let's try one. So we want to read our question. We want to identify these variables within that question, line everything up, plug it in, and solve. So what is the rate constant for a 0 order reaction when the initial concentration is 1.25 and the concentration after 48 seconds is 1.10 or 0.1? So lots of different information there. One thing to notice is that it specifically says it's a 0 order reaction. Okay, that gives you direction. It's telling you use this equation because this equation matches with 0 order. Okay, we've got to match the equation to the order. So we want to use our 0 order equation. It says, what is the rate constant? So we're looking for K. We don't know what that is. It says the initial concentration is 1.25. Initial is going to be our A at time 0. The concentration after 48 seconds, which is our time, is 1.01. So this is our concentration at that time, right? Those two kind of go together. So now that we've identified all of these pieces, we've got our equation. We can plug in, rearrange, and solve. So I personally, as you guys should know by now, like to rearrange before I plug in, just to make sure I'm getting all the letters in the right place. So key thing here, don't forget this negative. Make it extra dark for yourself so you know it's there. We want to solve for K. So we want to divide both sides by negative T. Okay, and that'll get rid of that negative and that T. Okay, so here's our equation. I'm going to take my concentration at time T, which is 1.01 molar. And I'm going to subtract my initial concentration of 1.25 molar. And then I'm going to divide it by negative time, 48 seconds. Okay, notice on the top these are in the same units, so we can add or subtract them. In this case we're subtracting, and then we're dividing by a different unit, so we'll have some things to analyze in terms of our units. All of this is going to be our rate constant, K. Just going to put that on the left so we can read from left to right. And then I'm going to do some calculating. I'm first going to subtract, get that answer, and then divide. So 1.01 minus 1.25, we know we're going to get a negative number from that. Okay, then we're dividing by negative 48, and we get a positive answer. You should always get a positive answer for all of these values. Okay, every value is a positive number. So that's something to keep in mind. Now, I've got 3 significant figures on the top. I've got 2 on the bottom, so we only get 2. 0, 0, 5. Now, my calculator doesn't give me 2 sig figs, so I can tack on that extra 0 to give me my 2 significant figures. And I've got molarity on the top. We're just subtracting them, so it's still molarity. And we're dividing by seconds, so molarity per second. All right, so molarity over time is our units of rate constant for K in a 0 order reaction. So that's helpful there. So that's our rate constant. This is another way of finding K. If we had a rate law with our rate constant, we can use this. This is the same rate constant, either in this equation or in the rate law. So the rate law for this reaction might look something like rate equals K times your chemical to the 0 power, right? And that would be 1. So rate equals K. That's our rate law. Same K value. All right, now we're going to take a look at first order equation. So that's our 0 order. Again, we can solve for any variable. We'll see some other examples of solving for other variables in these following examples. So first order reaction rates depending on the concentration of a chemical, a single chemical, raised to the first power. If the concentration of a chemical that is first order is changed, it will have a direct effect on the rate. For example, if the concentration of the reactant is doubled, the rate of the reaction will double. This is what we saw in our reaction orders activity we did. So the next equation on your equation sheet is the integrated rate law for first order reaction. So we're going to write that down. So when we look at our equation sheet, they are luckily in order. So it's 0, first, and second order. So the first order equation is the natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0 equals negative KT. Still with that negative there, so be extra careful with that. Okay, so a little bit different. What they did was they started with this equation, they did some calculus, and it popped out this equation. They did what's called an integral. So now we are going to use this equation. Anytime it's first order, we want to use this new equation with the natural logs. So let's take a look. You can always look at your equation sheet to refer back to it as well. So as you can see, all the variables are the same, but the equation is set up differently. All the same type of calculations can be made as were mentioned above in the 0 order reactions. So the only thing that's changing here is how we're plugging and solving, but the variables are all the same 4 variables. So let's take a look. A 4.5 molar sample of a chemical undergoes a first order chemical reaction. So this is our key here. It says first order, so that's telling us use the first order equation. That's your hint. What is the rate constant if the concentration of the sample is 2.13 molar after 126 seconds? So we've got a time, we've got a concentration of our chemical at that time, we've got an initial concentration, so at time 0 up here, and we're looking for the rate constant. That's our question. So I'm going to jot down our equation real quick so we can see it again. Again, you've got it on your equation sheet. You can always look there. Negative KT. All right. So we want to do some calculating here. We want to find that rate constant again. So if I want to find my rate constant, I'm going to do the same thing I did on my last one. I'm going to divide by negative t. So I'm going to have the natural log of AT. So I'm going to go ahead and plug that in, 2.13 molar minus the natural log of A0, 4.50 molar, divided by that negative t, negative time. Again, I want to make sure I'm making that negative really obvious for myself so I don't forget it. And that's going to equal my rate constant. I'm going to put it on the left there, make our setup go left to right. All right, now we want to do some calculating. Again, we just need to plug it into our calculator. Be careful, we do want to include these parentheses that are given and do this in some chunks. Your natural log button is right here. We've got logarithms and the natural logs. You should have looked at those in Algebra 2, pre-calc, depending on which one you are. So natural log of 2.13, close that parenthesis, minus the natural log of 4.5, close that parenthesis. I'm going to go ahead and do that subtraction so it's done in my calculator and it's not going to change any order of operations. Then I'm going to hit divide and divide by my negative 126. Again, you notice my previous answer was negative. This is negative. I'm going to end up with a positive answer. So similarly to our last one, we've got close number. We've got 3 sig figs on everything. So 0.00594 it looks like. And now let's talk about our units. When it's a first order reaction, our units for K are 1 over seconds. Oops, you guys can't see that. First order, our K's units are 1 over seconds. So how does that work out? Well, when we take the natural log and subtract it, another way to look at this, and you might remember this from math, this is the same as the natural log of 2.13 molar over 4.50 molar. So those molarities will cancel. Okay, I can show it to you. So let's go back up. This is my subtraction calculation, negative 0.7479. Okay, so let's keep that in mind. So if I set it up the other way, I get negative 7.7479. They are the same value. So you can set it up that way if you feel like, or you can do this subtraction. This is the way it's written on our AP exam. But in terms of our units, our molarities are canceling when we're doing that subtraction. Okay, they go away. So we're only left with seconds, which are on the bottom, 1 over seconds for first order. Okay, so that's the funky thing here is your units. So that's our rate constant. Now, it says, what is the concentration of the sample after 4 minutes? So we've got another time. We've got a rate constant from up above, so K is right there. We've still got an initial concentration because this is part of the same situation. So we want to know the concentration of a chemical after 4 minutes, after a specific time. So let's see how we solve for one of these pieces, all right? Now, we want AT, so I'm going to take my thing here. I'm going to say the natural log of AT. And this is being subtracted, so I'm going to add that term to the other side. So equals negative KT, KT, plus the natural log of A0, my initial concentration. Okay, so I took my negative KT and I added this term to both sides. Okay, so moved it over. Now this is the natural log of that concentration. This is not the concentration of AT, right? So I'm going to have to solve and then do kind of an extra step here. So just plugging in and solving is not enough. We're going to have to do another step. So let's go ahead and see what this would look like. So negative, my K value from above, 0.00594, 1 over seconds, times my time. It's in 4 minutes, and this is in seconds, so we've got to do a little converting here. There's 60 seconds in a minute, so 4 times 60 would give me 240 seconds. So I'm going to go ahead and change that, 240. This is 3 sig figs, so I'm going to do that. And then we're going to add to that the natural log of A0, which we have up here, 4.50 molar. All right, so we've got a lot of numbers happening here. I'm going to go ahead and say, okay, my natural log of AT is equal to, and let's simplify this side. I've got, let's do it over here. I've got negative 0.00594 times 240. When I do that, my seconds will also cancel. So we've got negative 1.4256. I'm going to leave that in there, and I'm going to go ahead and add my natural log of 4.5. Close those parentheses, and I get this. So I'm going to leave that number in my calculator. I'm going to write down some of the digits, 7, 8, 4, 7. I've got 3 sig figs, so I'm leaving an extra one there. And I'm going to go ahead and that's got a molarity on it. And then I'm going to go ahead and leave this in my calculator. Okay, we're not done calculating yet. So I don't want to round too early because we've solved for the natural log of the concentration is this. Now we need just the concentration. So we need just AT. So how do we do that? I'm going to switch my color here so you can see what's happening. The opposite of a natural log we can see on our calculator is e to the x, little e, okay? Not the same as our like scientific notation e. So I'm going to take little e and raise it to that power on both sides. Okay, so this is the power I'm raising it to. So when I basically do e to the natural log, it undoes this part. It's like they cancel each other, and I just get a. I just get my concentration, but I've got to do it to both sides. So I've got this number already in my calculator, haven't touched anything. So here's what I'm going to do. I'm going to hit second, and then this natural log button so I get my e. But now I want that answer I already had in there. So I'm going to hit second again, and then down here my answer button so that it puts in that previous answer. And here's my concentration. 1.08. We've got 3 significant figures on all our values. Molar, because it's a concentration, and that is our final answer. Okay, so again, I'm hitting second E, second, and then this negative button, which has A and S, that's for answer, so it puts in your previous answer. So that's how we undo a natural log, okay? We're doing the opposite there. So that's a little skill. Play with your calculator, try it out. Now we can check ourselves. Does this make sense? Okay, well, after 126 seconds, we had this concentration, right? We started with 4.5. After 126 seconds, we had 2.13. Does it make sense that after more time, 240 seconds, we should have a smaller concentration? Yes, because over time, right, our concentration of our chemical over time is always going to decrease. Always. Okay, so we should get a smaller concentration for AT. AT should always be smaller than A0. Okay. So that's a couple things we can calculate there using our first order equation. You can calculate this with 0 first or second order equation. It just depends on our setup and how we're going to solve. Okay, let's take a look at second order. So I know this is a little bit longer video, but we got a lot of equations to learn. Okay, second order reaction rates depend on the concentration of a single reactant. That is an extra blank. We don't need that. Raised to the second power, or on the concentration of 2 reactants, each raised to the first power, right? So we've either got A to the second, or we've got A to the first and B to the first kind of thing. Those are second order equations. If the concentration of a chemical that is second order is changed, it will have a squaring effect on the rate. For example, if the concentration of the reactant is doubled, the rate of the reaction will be 4 times faster, right? Because doubling the concentration and it's squared because it's second order gives us 4. If the concentration is tripled, then the reaction will be 9 times faster because 3 squared gives us 9. So the second equation, this should be the third equation from your equation sheet, is the integrated rate law for the second order reactions. Again, from our sheet, it goes 0 first, second order. Second order is 1 over the concentration of AT minus 1 over the concentration of A0 equals KT. So this one is not negative KT. It's different there. So again, to find this equation, they took our first order equation, did some calculus, popped this one out. Now we can use this one. This is second order. So here's our example for this. A reaction has the following rate law that was determined through experimentation. So they give us the rate law. By giving that, we can see that it's second order. Okay? So that's the way they're telling us, hey, use the second order equation. Okay, somewhere in the question, they're either going to state that it's something like in our previous one, they stated it's first order, or they're going to give us info to find out that it's what the order is. The concentration of chemical X is determined to be 3 molar after 25 seconds. So this is our concentration after a time. If the initial concentration is 10 molar, what is the rate constant of the reaction? So we're looking for rate constant again. So let's go ahead and take a look at our equation. We've got this equals KT. We've got some fractions here, so we've got to be really careful with how we deal with those. Equals KT. So we want to solve for K, so I'm going to divide this whole thing by T. So I've got 1 over my concentration at a time, 3.0 molar, minus 1 over my initial concentration is 10 molar. I'm dividing all of that, so I got fractions on fractions, by my time, which is 25 seconds. And that's going to all give me my rate constant. Okay, let's do some math. We got to be careful here. I'm going to put these parts in some parentheses just to make sure that my fractions are working out. So I've got 1 over 3 minus 1 over 10. And I'm going to go ahead and hit enter. And then I'm going to divide that value by 25. And we get this. 0. We've got 3 sig figs on everything. 0.00933. And let's take a look at these units. This is 1 over molarity, 1 over molarity. So those molarities are on the bottom of the fraction. These seconds are on the bottom of this larger fraction. So 1 over molarity times seconds. And those are the units for my rate constant. That is second order. All right, second order should have only one molarity on the bottom. So that's how we can find our rate constant. We can answer any other question with this. You've really got to be careful with these fractions though, okay? If we wanted to solve for AT or A0, you got to remember that it's a fraction. So let's just pretend I want to find AT. Let's look at that real quick as a little side note. So if I wanted to find this value, they're being subtracted. So I would add this one to the other side. So I get 1 over AT equals KT plus 1 over A0. You're not done though. This is a fraction, right? So if I was to plug in my numbers and solve for that, I have solved for 1 over the concentration of A equals some number. Let's call it 1,000. Whatever it is. Okay? So you haven't finished though. You need just the concentration of A. Well, it's the reciprocal, right? So I can flip both sides and get my number. I'd have A T over 1 equals 1 over 1,000, whatever my number is. So then I would have my concentration of A. 1 over 1,000, which is 0.0001. No. I feel like I have not enough zeros. Oh no, I have too many zeros. 0.001, okay, with your units. So that's a way you can think about this if you're trying to solve for one of these concentrations. Be careful with that. When you solve for that piece, you're solving for the reciprocal. Flip both sides and solve that way, okay? It's just a little side note. Okay, last part of this. Again, I'm sorry this is a long video. We got a lot of equations, 4 equations just to look at. Our last one is called half-life. Now, this is only for first order. So when you're talking about half-life, they're really only going to talk about first order equations. So the final equation given on the equation sheet concerns half-life of a reaction. Half-life is the time it takes, so it's half-life is a time for the concentration of a chemical to decrease by half. So we're cutting the concentration of in half, and we're looking for the time. The equation was found by simplifying the first order integrated rate law above, as shown above, or shown below, my goodness. So if we had that natural log equation, the same first order one on that list, and I put in the initial concentration as 1, and the final concentration is half of that, 0.5, it simplifies to negative 0.693, always. Okay, and that would equal negative KT. So if I put in 2 and 1, or I put in 17 and what is half of 17? 8.5, whatever those two values were, we're going to get the same number. Okay, because it's always cutting it in half. So they've basically simplified the equation for you. That equals negative KT. So if we drop the two negative, or we divide by negative K, we get the time it takes for half the concentration, T1 half. This is what is shown on your equation sheet. Okay, so this is great because if we're given half-life, we can find our rate constant really easily. Or if have our rate constant, we can find the amount of time it takes to cut the chemical in half, its concentration. So let's just take a look more at half-life. This is only used for first order reactions because their half-life is constant. And we can see that in the graph below. You can find your half-life, or that time, by finding the initial concentration and then the time it takes to reach half that value. So if my initial concentration is 2, then we'd want to figure out how much time it takes for it to be cut in half. So 2 would be cut in half to 1, and it takes 80 seconds. Okay, so my half-life equals 80 seconds. That means every 80 seconds, the concentration is cut in half. If I do another 80 seconds, now I go from 1 to 1/2. I do another 80 seconds, I go from half to a quarter. I do another 80 seconds, now I'm at half of a quarter, which is an eighth. And then another 80 seconds is another half-life. So each of these is a half-life. So this chemical goes through 1, 2, 3, 4, 5 half-lives. So if we know how long it takes to go through one half-life, we can figure out how long it takes to get to a specific amount of chemical, which is great. So it says, what is the concentration after 4 half-lives? So if my initial concentration is 2 molar, cutting it in half would give me 1 molar. In half again would give me 0.5 molar. In half again would give me 0.25 molar. So this is 1 half-life, initial, so 1 half-life, 2 half-lives, 3 half-lives. And then we do one more. 0.25 divided by 2 would give me 0.125 molar. So that would be my concentration after 4 half-lives, after I've divided in half 4 times. If we have a graph, we can use our graph, all of that. And if we wanted to know how much time that took, we could say this, each of these is 80 seconds. So 80 times 4 would give us how long it takes. So this would take 320 seconds to get to that concentration. So there's ways we can kind of use logic through these different ones. Now, if it says what is the rate constant of a first order reaction and they give us a half-life, we can find our rate constant using our equation. Half-life equals 693 divided by our rate constant. So we can always rearrange this. If we want to find K, we can multiply by K, both sides, and then divide by our half-life. So our K's cancel. So if we want to rearrange this, basically K and T1/2 or half-life end up switching places. So keep that in mind. These two just switch places from the original equation, simplifies things. If our half-life is 57 hours, then our rate constant would be 0.693 divided by 57, and we get 0.0122, 1/hours. Our rate constant units are always 1/time for first order, which we get here. So, the final question before you get to your practice, which equation do we use? You're going to read the question, and it will indicate somehow, either through stating it or giving a rate law with the order, what the order is. Then you choose the equation that matches the overall order of the reaction. If it discusses half-life, we're going to be looking at first order. So, for example, if I look at number 1 here, the reaction between sucrose and water produces fructose and glucose is a first order reaction. So we would be using a first order rate law or integrated rate law, the one with the natural logs. Okay, if you looked at another question, if I flip to number 6 here, first order, Where's one that's not first order? A lot of them are first order. Here's one. So number 2 gives us a rate law there. It's second order. So we're going to use the second order equation for that one. All right. So that's how we approach these. That's how we do these equations. You've got your 4 equations on your equation sheet. Try it out. Let me know where we're getting stuck, what questions we have, and have a great day.